Okay, so let us continue with the chapter Chemical Bonding and Molecular Structure, chapter 4. So in the morning class, I was talking about the properties of ionic compounds. Okay, so now on the basis of the properties of ionic compounds in this afternoon class, I would like to just discuss with you a very important cycle, which is known as Born-Haber cycle. It is known as Born-Haber cycle. Okay, now what is Born-Haber cycle? Now this Born-Haber cycle, it is a cycle which helps us to understand and calculate the energy change. It helps us, this cycle helps us to know the energy change involved in the formation of an ionic bond, from where? From its constituent elements, Okay, so this is called the Born-Haber cycle. Now this Born-Haber cycle helps us to understand or know the energy change which is involved in the formation of an ionic bond from its constituent elements. Okay, now let us take one example and try to understand this Born-Haber cycle. Let's take for the formation of sodium chloride. During the formation of sodium chloride salt. Okay, now here for the formation of sodium chloride salt, we need sodium atom which is solid. Okay, and we need chlorine gas. Which is in the gaseous state. Now from this chlorine gas we need only one chlorine atom, so I'm writing over here half. Okay, try to pay attention. Now let's go step by step. This sodium metal in the solid state, it has to be sublimed. So I will write over here sublimation. So there is heat of sublimation. So delta sublimation H naught. We have to give heat plus. Okay, then this sodium atom becomes in the vapor state. It becomes sodium in the gaseous state, G. Okay, this is the first step. Once we get the sodium atom in the gaseous state, now we must knock out the electron from the valence shell to remove the electron. So that comes under ionization. Removal of electron, minus electron. So this is ionization energy or ionization enthalpy. This is also positive because we are giving heat. It is the heat required, so plus sign. So once the electron is removed from the valence shell of sodium atom, gaseous, this sodium atom becomes sodium ion in its gaseous state. Okay, now we stop over here for sodium gas ion and come down to chlorine. Now this chlorine molecule has to be dissociated. It has to be dissociated over here. So we have to allow it to dissociate. So dissociation. Now the energy involved over here, it is half delta dissociation, DISS H naught. This is also plus. We have to provide energy, we have to give energy required by the chlorine molecule to split into chlorine atoms in the gaseous state. So After providing so much of energy, half of this energy,
Mhm.
it becomes, yes, chlorine gas.
So
Pardon?
why did we put that off?
Because chlorine gas, it exists in the diatomic form, no? Chlorine gas
Yes,
exists in the diatomic form. That's why you have to break down into its atomic form, gaseous atomic
yes,
form.
sir.
Are you getting it? After that, once we make chlorine atom in the gaseous state, now we have to give it an electron, give the electron, E minus. That is enthalpy, what do you call? That is enthalpy over here, electron gain enthalpy, EG. Electron gain enthalpy, this is the symbol. And here, energy which is liberated, so minus over here. Okay. So this will give me a chloride ion, Cl minus G, chloride ion. Okay. Now this Na plus and this Cl minus, they will combine to form 1 mole of sodium chloride crystal. So that is the lattice energy which is given out. U stands for lattice energy. Okay, this is the lattice energy. Okay, crystal formation. Crystal formation takes place after this only. Crystal formation, and then we get sodium chloride crystal. So this cycle which you see over here, no, it is called the Bond Haber cycle. It is called the Bond Haber cycle. Now, from this formula, no, from this Bond Haber cycle, we can derive a formula for the amount of heat liberated, for the amount of heat liberated in the overall reaction, there is a formula. I'm going to write it down, and that is represented by delta H naught F, heat of formation. This is called enthalpy or heat of formation, is equal to, we have to add this one, that is plus sign delta sublimation H naught, okay, plus this one ionization enthalpy, plus half of dissociation enthalpy. Okay, then over there, after that, we have this is electron gain enthalpy there, electron gain enthalpy. Okay, that is, you have to put it over there. Electron gain enthalpy, I put over there, plus uh, delta Eg H naught and plus U. So this is the formula to calculate the heat of formation of sodium chloride. Enthalpy of sublimation, ionization energy, half of dissociation energy, plus electron gain enthalpy, plus lattice energy. And if in the numericals, the symbols for the lattice energy is minus, so minus will enter over there. Okay, minus will enter in the lattice energy also here. So you can accordingly calculate and get the value of delta H naught F, heat of formation. Okay. Now to understand this, let me do a problem. Okay. Please have a look at the formula carefully. Okay. Have a look at the formula carefully. Okay. So this is the formula you have to remember. You have to remember this formula. This is the formula, important formula. Delta H naught F, heat of formation, is equal to delta H naught sublimation plus ionization enthalpy plus half of dissociation enthalpy, plus if it is a diatomic gas, then it's half, plus enthalpy of electron gain enthalpy plus lattice energy. Okay, now to understand this properly, I will do one numerical. Okay, so the question goes like this. Okay, a numerical question goes like this. The question says calculate the heat of formation of sodium chloride from the data below. Okay, now the data is given over here. The value of delta sublimation H naught for sodium it is given 108.5 kilojoules per mole. Okay, that is called heat of sublimation for sodium. Then next one is chlorine dissociation, because sodium chloride, no, chlorine, so you write over there uh, dissociation energy of chlorine. Dissociation energy of chlorine, that is delta DISS H naught. Okay, its value is given 243.0 kilojoules per mole. This is the part of the question. Okay, then ionization enthalpy, energy of sodium. Ionization energy of sodium is given to be 495.8 kilojoules per mole. Okay, then electron gain enthalpy. Electron gain enthalpy of chlorine. Chlorine is given as negative. Okay, 348.8 kilojoules per mole. Okay, then lattice energy. Lattice energy of sodium chloride, NaCl, that is symbol is U. It is given as minus 758.7 kilojoules per mole. Okay, so these are the data given. So now, by using the formula directly, we know the formula. We know the formula is delta H naught formation. The heat of formation is equal to delta sublimation H naught plus ionization energy plus half of dissociation energy plus electron gain enthalpy plus U. Now just put the value directly over here. Delta H naught sublimation, it is given 108.5 plus ionization enthalpy is given 495.8 plus this value is given 243. So 243 will be divided by 2. Okay, so 243.0 divided by 2 plus electron gain enthalpy is given how much? Minus 348. So I'll put over here minus 348.8 plus lattice energy is given minus 758. So minus 758.7. So if I simplify this, then I will get the answer. Answer is coming to minus 381.7 kilojoules per mole. So this is the heat of formation of sodium chloride. Okay, so this is the application of Born-Haber cycle. This is the heat of formation of sodium chloride. So this is how you'll get numerical, direct formula based numericals based on heat of formation. Okay, am I clear, boys? Am I clear? Am I clear?
Yes, sir.
Formula you put the heading.
Yes?
Yes, sir.
Formula. Anything with the formula? Heat of formation is equal to heat of sublimation, ionization enthalpy, half of dissociation enthalpy, electron gain enthalpy, and lattice energy. All positive sign over here, okay? And this negative sign is entering as according to the dissociation, or what you call this electron gain enthalpy and the lattice energy. Okay. Now, so this has been represented in a diagram over here for you all again. Okay. And then we have numerical. Diagram based numerical over here. See the delta H sublimation The delta H sublimation is given 108 kilojoules per mole. Okay. Ionization enthalpy is given 496 kilojoules per mole. Okay. Then dissociation is given plus 122. Okay, half of chlorine directly it is given. And after that, electron affinity is given minus 349 over here. And then lattice energy is given minus 788. So just put the value directly, you'll get the answer for this minus 411 kilojoules per mole. Okay, so that is how you solve problem based on the bond Haber cycle and its formula for the calculation of heat of formation. Okay, now let's go further now to covalent bond. What is a covalent bond? Okay, what is a covalent bond? A covalent bond, we know it is a bond which is formed between two atoms, non-metallic atoms, by mutual sharing of electrons. Mutual sharing of electrons to gain the nearest noble gas configuration. Then the bond is called covalent bond. Okay, so to gain the nearest noble gas configuration. So it becomes a covalent bond. The example is given over here. Sharing of electrons between carbon and hydrogen to form methane molecule. Okay, that is one good example over here. Going to the next slide. A covalent bond, if you see, is a chemical bond in which pairs of electrons are shared between two atoms, non-metallic atoms. The covalent bond is also called a molecular bond. It is also called a molecular bond. The forces of attraction or repulsion between two atoms when they share electron pair or bonding pair is called a covalent bond. So electrons, they come. There might be forces of attraction, there might be forces of repulsion. So both these forces of attraction and repulsion are responsible for holding the two atoms together. That's how it becomes a covalent bond. Carbon, having 4 electrons in its valence shell, has given it the ability to form innumerable molecules and bonds. This is why carbon has so many elements and allotropes at the same time. Okay, so this was about introduction to covalent bond. Moving to the next slide, let's understand the bond parameters. So bond parameters are nothing but they are some points with the help of which we can understand the different attributes related to bonds. Okay, so now covalent bonds can be characterized. They can be characterized on the basis of several bond parameters. The first one is bond length, then there is bond angle, then there is bond order, bond energy, also known as bond enthalpy. Okay, these bond parameters offer us insight into the stability of a chemical compound and the strength of the chemical bonds holding the atoms together. So with the help of these bond parameters, we come to know about the stability of a bond or the strength of the bond, okay, with which they are held together very strongly. Then the first bond parameter is called bond order, BO. In short, we write it as BO, bond order. Okay. Now, the bond order of a covalent bond is the total number of covalently bonded electron pairs between two atoms in a molecule. It can be found by drawing the Lewis structure of the molecule and counting the total number of electron pairs between the atoms in question. For example, between hydrogen atoms in a molecule, there is a single bond, so its bond order is 1. If we talk about a double bond, in oxygen molecule, there is a double bond. Okay, so bond order is 2. Triple bonds have a bond order 3. So if you talk about nitrogen molecule, there is a triple bond. So bond order is 3. So did you understand bond order, the first parameter? Did you understand bond order? Hello, can you hear me? Can you hear me? Did you understand bond order?
Sir.
Okay, so the number of bonds,
Sir.
number of covalently bonded electron pairs which is present between two atoms in a molecule is called the bond order. So single bonds bond order is 1, double bond order is 2, triple bonds bond order is 3. Then the next parameter, the second parameter is called bond angle. Bond angle can be defined as the angle formed between two covalent bonds that originate from the same atom. Now, illustration detailing the bond angle in water molecule. I'll just show it to you. It is not shown over here. Water molecule, if you see, this is water molecule, okay? There are two lone pairs like this, okay? Now, this angle is 104.5 degrees. Okay, that is water molecule. If you look at ammonia molecule, NH3, this is a lone pair. Okay, so in NH3, the bond angle becomes more. It becomes 107 degrees. And if you look at methane, say I draw methane, carbon, hydrogen, 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 hydrogen. Hydrogen here, hydrogen here, hydrogen here, hydrogen here. So over here, in carbon and methane, the bond angle over here, it becomes 109 degrees, 28 minutes. Okay. So this is called bond order. Okay. So this bond order, the geometric angle between any two adjacent covalent bonds is called a bond angle. This bond parameter provides us information into the molecular geometry of the compound. So with the help of bond angle, we can find what? You can find the molecular geometry of the compound, whether it is a linear molecule, or it is a bent molecule, or it is a tetrahedral molecule, or it is a trigonal planar molecule, and so on. Okay. Now, moving to the next parameter, bond parameter. If you look at the next bond parameter on your screen, you can see bond length, the third one. Bond length, it is a measure of the distance between the nuclei of the two chemically bonded atoms in a molecule. It is approximately equal to the sum of the covalent radii of the two bonded atoms. Sum. For covalent bonds, the bond length is inversely proportional to the bond order. Higher bond order results in the stronger bonds, which are shorter, accompanied by stronger forces of attraction. So short bonds are a consequence of these strong forces. Suppose you have a carbon-carbon single bond. This will be longer. If you have a carbon-carbon double bond, it is shorter. If you have a carbon-carbon triple bond, it is much, much shorter. So among these, the longest bonds are the single bonds, slightly smaller is shorter is double bonds, and shortest is triple bonds. Okay, so the bond length depends upon the bond order as well. Now, moving to the fourth parameter in covalent bonds, which is called bond energy or bond enthalpy. Bond energy is a measure of the strength of a chemical bond, how strong a bond it is, the energy required to break or make a bond. It can be defined as the energy required to break all covalent bonds of a specific type in 1 mole of a chemical compound, which is in its gaseous state, obviously. It is also important to note that bond energy is not the same as bond dissociation energy. Because if you look at the definition, energy required to break, bond energy is the energy required to break. Okay, it is different from bond dissociation energy. The latter, that is bond dissociation energy, is the change in enthalpy, the energy which is involved with the homolytic cleavage. When two break homolytically, hydrogen molecule, if you break them homolytically to form radicals like this, that time it is a homolytic cleavage of a bond, whereas the former is the average of the bond dissociation enthalpies of all bonds of a specific type in a molecule. So these are the four important bond parameters which are associated with covalent bonds. Now, under the fourth parameter, we must understand the factor affecting bond energy. That is important. The strength of a chemical bond is directly proportional to the amount of energy required to break it. So more the energy required, stronger is the bond. Therefore, bond energy is inversely proportional to the bond length. If the bond length is longer, then this bond energy will be less. That is, longer bonds have lower bond energies. Please learn this. The bond energy is directly proportional to the bond order. If it is a double bond, triple bond, bond order is high, so the bond energy will be higher. Multiple bonds have high bond energies. Learn this also. The third one is The bond energy is inversely proportional to the atomic radius of the atoms participating in the bond. That is, since the atomic radius is directly proportional to the bond length, so this and this are almost similar. So atomic radii, if it is short, then the bond energy will be higher. Okay. So note that the difference in the electronegativities of the atoms participating in the chemical bond is also contributing to the bond energy. So that is also very, very important. If the electronegativity difference is minimum, then the bond energy is going to be higher. It is going to make the molecule more stable. Okay. So these were the factors with respect to the covalent bonds and bond energy. Now have a look at the next slide over here, just to understand bond energy, bond order over here. This carbon triple bond order is 3. Carbon single bond over here, bond order is 1. Carbon double bond order is 2. Okay, but here carbon oxygen, it is a partial double bond. So bond order will be 1.5 approximately. It is not exactly 1.5, it is approximately 1.5. So I think the idea of bond order is very clear to all of you now. Okay, now after this, let us understand the bond angles also in the next slide. Okay, if the bond angle, learn this also. If the bond angle is 180 degrees, then the molecule have a linear geometry shape. If the bond angle is 120 degrees, then the geometry of the molecule will be trigonal planar. If the bond angle is 109 degrees 28 minutes roughly, it will be tetrahedral like methane molecule. If the bond angle is 120, one of them, another one is 190 only, then it is a trigonal bipyramid. Okay, it will be a trigonal, but 120 and 90 has to be there. One side 120, this will be 90. Okay, and if the bond angle everywhere, it becomes, this is above the, if you put a plane over here, okay, this is above the plane, this is below the plane, and this is on the plane. This is on the plane. That time, if this bond angle is 90, then it becomes octahedral geometry. So I want you all to learn this chart. With respect to the bond angles. If I give you the bond angles in the examination, then you should be able to tell me or write down the geometry of the corresponding molecules. Okay. Now, moving to the next slide, we have the parameter, one of the parameters of bond length. Have a look at it very, very carefully. In a covalent molecule, Ra plus Rb, radius, atomic radius of A is Ra. It looks smaller, and Rb is atomic radius of B. So they are bonded covalently. Okay, that is called an bond. That is the covalent bond. Distance from the nucleus of A to the nucleus of B. That's a covalent bond. For a single bond, normally carbon-carbon single bond has a bond length of 154 picometer, 154 into 10 power minus 14 meters. Double bond is 134 picometer. Triple bond becomes shorter, 120 picometer. So try to remember this also. Carbon-carbon single bond, carbon-carbon double bond, and carbon-carbon triple bond, the bond lengths, this parameter, okay, the value. Now, if you look at the next slide, bond enthalpy definition has been explained on the basis of a diagrammatic illustration. If there is a molecule formed out of AB, and if the molecule breaks down homolytically, electron here, one electron here, so the energy required, the energy which is involved to break them into fragments like this, molecular fragments which are stable, that is called bond enthalpy. Okay, now coming to the next slide over here, covalent bond Lewis structures. Water molecule has oxygen atom has 2 lone pairs. Okay, ammonia molecule, nitrogen has 1 lone pair. Okay, this is the Lewis structure of carbon dioxide, Lewis structure of nitrogen. Okay, you can draw the Lewis structure of oxygen as well. Oxygen, each oxygen atom has 2 lone pair of electrons. This is something which you have learned in class 10 also. Okay, now after this, have a look at some more, plenty of other examples. Lewis structures, carbon dioxide, forming covalent bonds. Okay, carbon dioxide. This is the final structure. Then nitrogen, formation of nitrogen. This is the Lewis structure. Formation of bromoethene, double bond is there. Then formation of iodoethine. Of course, these two are important. Okay, this is formation of hydrogen cyanide. HCN, hydrogen and carbon single bond, carbon and hydrogen triple bond. So try to remember this. H, C, triple bond, N. Okay. So these are some Lewis structures which you should try to remember and must be able to draw when it is asked in the examination, because questions have been asked from this also. Now, moving to the next subtopic in this chapter under the heading covalent bonds, covalent compounds, polar character of covalent bonds. If you look at this molecule over here of chlorine, these chlorine atoms are equally electronegative. They are what? Equally electronegative. These two electrons present are exactly in the center, equally distributed between the two chlorine atoms over here. Okay, that's why this chlorine molecule becomes a non-polar covalent bond. The bonding electrons are shared equally between two atoms. No charges are on the atoms. You will not find any charges on the individual carbon atoms. After that, look at number B. This is hydrogen chloride molecule. This hydrogen chloride molecule, okay? This in here, sir. Keep it here, sir. Okay. Okay, sir. This is hydrogen chloride molecule. Here in hydrogen chloride molecule, you see that the electronegativity of chlorine is much higher than hydrogen. That's why it will pull the two electrons towards chlorine. It pull the two electrons towards chlorine. That's why this chlorine will carry a small negative charge, whereas the hydrogen will carry a small positive charge. As a result of which this bond between hydrogen and chlorine becomes a polar covalent bond. The bonding electrons are shared unequally between the two atoms. Partial charges on atoms are seen. Okay, that is number B. Then you come to number C, a purely ionic bond. Purely ionic bond. In an ionic bond, there is complete transfer of one or more valence electrons. Full charges on resulting ions are seen. So that is how we can have an idea about the polar character of covalent bonds. One is non-polar, this one is polar, and this one is ionic bond in ionic compounds. Okay. Now, have a look at some more shapes of covalent bonds. Linear. I think now you know the angle. Angle you know. Angle you know. Bent or angular you know. Tetrahedral you know the angle. Trigonal bipyramidal 90 120. Okay. Octahedral 90 90 90. Okay. So this, try to remember this figure also. It will help you in answering plenty of questions. Okay. Now, look at the next slide. An important slide. Formation of sigma bonds. When the SS orbitals overlap, okay, it forms always the overlap of SS orbital. S orbital, another S orbital, always result in the formation of sigma bond. And if the S orbital and the PZ orbital overlap head on, this is overlapping head on, head over here, then it forms a sigma bond. SP overlap head on, SP S overlap head on, PZ PZ head on, all sigma bonds. This all result in the formation of sigma bond. That means if the orbitals are overlapping head on, when I say head on, it means like this. Let me show you. Let me show you. Can you see the screen? If the orbitals overlap this way,
Yes, sir.
if the orbitals overlap this way, this is called head-on overlap, and this results in the formation of sigma bonds. Okay, but if the orbitals overlap this way, if the orbitals overlap this way, sideways, then they will result in the formation of pi bonds. Head-on means sigma bonds, sideways means it is forming pi bonds. Okay, now let us come back to the slide over here, our slide. Okay, now please try to remember this formation of sigma bonds. Moving to the next slide over here, formation of pi bond, okay. P atomic orbital, they are overlapping sideways. I have told you, no? Sideways, they are overlapping sideways. So it will form a pi bonding orbital in the molecule. So the symbol for pi bond is like this. If there is a carbon-carbon double bond like this, one is a sigma bond, another one is a pi bond. If there is a carbon-carbon triple bond like this, one is always a sigma bond, the other two are pi bonds. If there is a carbon-carbon single bond, then this single bond is always a sigma bond, which is formed by the head-on overlap. So for sigma bonds, remember, it is result of head-on overlap, head-on overlap of the orbitals. But if it is formation of pi bond, it is not head-on, it is sideway overlap of the orbitals. Okay, so you have understood the formation of sigma bonds also, you have understood the formation of pi bonds also. Okay, now it is almost time, it is already time up, so I'll like to conclude in my class here only. I'll continue with the next class tomorrow in the same time, from 12 o'clock till 12:40. So just hang on over there. Let me first record your attendance only, then you may leave the class. Okay, just hang on, let me save the document. Okay, I'll record the attendance now. Attendance is downloaded. Now you may leave the class. Have a nice day. Thank you so much.
Thank you, sir.